Okay, let's go ahead and get started. In terms of where we are, you had Monday off. You had a couple Mondays before that off because it wasn't the semester. I have posted your Lab 1. Originally that was due before next class, but I punched it back a couple days because I want you to have 2 class periods to work on it. Now, that does not mean, though, that you will not have sufficient class time to solve it solely in class. So what I want part of today and then part of next Wednesday or next Monday to be is I'll be walking around. You should be working on Lab 1. I will help you with Lab 1. But I will also start some of the timer assignments next Monday. So if you haven't finished Lab 1 by then, you're going to have something else sitting on top of it. So really put in some time and effort today, and especially sort of the remainder of this week. So tomorrow I have a large set of office hours between 1 and 3. I can also come in, maybe, like Pizza Friday. Like if you need me to come in, I can come in. We can email. Please make sure you're working on this, and then if you've got difficulties on it, you contact me. It's a non-trivial assignment. It's not really that hard, but you're not going to be able to bang it out in an hour or two unless you've just been really following along. One thing about Lab 1, the buttons are called PB0 and PB1. That does not mean that the buttons live at port B0 and port B1. It's a terrible way that the user sheet calls it, or the user manual calls it, but that does not denote the location of the button inside the processor. You're going to have to use the user manual and manually look it up. And kind of seeing where people are, who's able to blink a light using the library calls? All right, okay, so most everybody. Who can blink a light using sort of the data structure? Okay, and who can blink a light manually with all the pointer stuff? All right, really got to get into and get through the pointer stuff today. Because the final part where you have to turn a button on and off, you have to turn the light on and off, and you have to keep a light illuminated as long as the button's pressed. That requires a small algorithm and an understanding of the code. So you need to be able to get there hopefully by the start of class next Monday so we can talk about it, or you come capture me in office hours. Questions so far as to that? Let me make this thing level. All right. It's going to be really funny if it falls off, while I'm talking. I have all of your assignment ones. What were people's thoughts on that? Did you find it hard? Did you find it difficult? Easy? Okay. I will get to those, and I will grade them by the end of the week, so you can have that. Let me see if I have my solutions. So let me quickly just kind of go over a couple of the solutions that are important. Chip init just starts up the processor and removes any hardware errors that might have existed. So you never make a chip perfectly. The design is never perfect. Over time, they've discovered some errors, and they're trying to resolve those errors via software. So it's sort of this patch that has to be up, because you can't fix the hardware. It's a software patch that gets applied every time you boot. Your variable sizes. It is a 32-bit system. So that means that generally all of your variables are going to be 4 bits or 4 bytes long. So an unsigned int, a long, a float, a char, an unsigned char is usually a byte. So you'll see in a lot of embedded systems, people will use unsigned char in place of a byte. You're not always guaranteed that that's how they implement it, but an unsigned char is usually a single byte. Even the pointers to your objects are 4 bytes, even if they are longer objects, because you're still pointing to a 32-bit memory address. You only still need 4 bytes to do that. The only thing that is super long is a double. So a double is a double length floating point, or a double precision floating point. That's why it's 8 bytes. There's also a type called a long in some systems, and that will be an 8-byte integer. So you can have an unsigned long. It's just giving yourself more bits and more values that you can implement. The memory map, so what you should have been able to do here is to go through the program and figure out where stuff lives. Flash is in the lower part of the memory. It is still a Harvard architecture because there are physically separate memories for program and data. They live in separate memories. They have separate buses. Even though the memory map makes them look like they are in the same place, they are not physically stored in the same place. There is a special section of RAM that you can put the program. So the program is normally pulled from Flash, but if you want to access it quicker, you can copy and paste your program out of Flash into RAM. Sometimes during the bootloader will automatically do that for you. It costs you a little bit of RAM space, but it makes you access your program a little faster. What you should have found is that your global variable gets put at the start of RAM. It's right there on the heap. It starts at about 2008C or 200,008C. It's right there at the lower part of RAM. When you have a local variable that gets placed in a different location, that's technically up at the bottom of the stack because you're in a main function. It's a local variable. It is somewhere actually in the stack that you can access. Remember, in terms of your memory, the stack grows down as you push functions and variables, and the heap is sort of for your global and static variables. The heap is more important in a dynamic memory allocation system like any other desktop computer, but we do not do dynamic allocation on an embedded system because it puts in undetermined or non-deterministic abilities. If I'm swapping data structures in and out of memory, am I going to miss something? Am I going to run out of memory? What happens? So you should have found main is located in Flash. It's part of the program. It should be located inside the Flash memory. Important things about the structs. Remember, the structs are laid out contiguously in memory. So if I'm pointing to the top of the struct, and let's say it's at 100, and I have a 32-bit object immediately in the struct, the end of that object will be 4 bytes away. So everything inside the struct is contiguously laid out in memory and will be in order. And that is how we get the data structures for the GPIO, the timer, everything else we use. They're always structs because they're always laid out linearly in memory. Bonus question. I think 1 or 2 people have tried it. If you looked up in the memory map where the main function was located, it said it was at 2E8. If you drew a pointer to it, it would show that it's at 2E9. This is not a lie. Fundamentally, what's going on is that there are 2 types of instructions that the processor can run. There are thumb instructions and there are ARM instructions. And the lower bit of a function pointer is set to 1 if it's a thumb instruction. So that's how even though it's listed at 2E8, the lower bit is set to tell the processor that I want you to go to this location, but it's actually of a different instruction type. Not an easy thing to figure out, but if you kind of Googled around and you found out that there were 2 instruction sets, you could have figured it out. Questions on this? All right, this is a pretty easy introduction to the processor, the memory map, and how things are laid out. So over here. What I want to do now is I want to start moving into the different peripherals that you've got. So we've talked about GPIO, and now we're going to move into timers. And you can work on your labs if you want, but you're going to miss a whole hell of a lot of stuff on timers. So timers are another peripheral that you've got. on your processor. Go onto the Schoology page, pull up application note 14, which should be about timers. Read pages 2 through 5 really quickly and tell me 3 important things that you learned. 3 important facts. So if you go to data sheets, go back out, Ben. So if you go to 370 on the, go back out one more. There on the main page there's a folder called Application Notes. You want Application Note 14. Look at just the opening pages here. Give me 3 facts that you've learned or that you figure out about timers. All right, let's see what folks kind of figured out, kind of quickly looking. Kyle, what's something you figured out? Just very basic thing. Okay, so the timers on the system sort of have a variety of purposes, and something we're going to talk about is some of the modes that they can be in. There are way more many modes that these timers can be put in than we will actually sort of ever use. Michael, what's something you found out? Okay, so they can measure it or create it. Okay, so a very important property of timers is that they can do pulse width modulation. So what that is in a PWM signal is a square wave with a varying duty cycle, and there are a lot of purposes for that. You can, in general, fake an analog voltage, any analog voltage, with a PWM signal. So if you want to generate an arbitrary analog wave, you can do that by varying a PWM signal. At the same time, there are a lot of sensors that will generate a PWM signal that indicates some sort of process. So maybe you're measuring RPMs, maybe you're measuring speed. That comes out as a PWM signal. You don't want to write code that is constantly going, did my bit change, did my bit change, did my bit change? You would rather stick the timer to do that on their own. Darren, what's something you found out?
So more bits if you have 3 timers.
Okay, so how big is each timer?
16 bits.
Okay, so each timer is 16 bits wide. That means it can hold 16 bits of a number. If you need to time more things, if you need to store a larger value, you can cascade the timers to get 64 bits. So you can string them all together and put them together. I guess it's 68, but it's 16 times 3. All right, Jason, one last thing. What else did you find out? Something we don't have. Right, all right, that's another important thing. Your timers can have a variety of clock inputs. So you can drive the timer from the internal clock, from the peripheral clock, from an external clock. There are 4 or 5 different sources that you can drive the clock from. You can scale all of these clocks. There are a lot of options when it comes to timers, because timers are used almost everywhere inside of your microprocessor. So, important thing, you've got 3 16-bit timers. You can cascade them together into other sizes that you like, so 32 or 48 bits. The very basic modes of your timer are that they simply just count up and they roll over, or they count down and they underflow. So they can count up, they can count down. That's sort of the basic mode. There are more advanced modes where you can set limits on them, and they'll go up, they'll go down, they'll go sideways. And we'll cover a couple of those, but the basic modes are simply count up until some number and then let me know when you get there. Another thing is that the timers are only useful if they can trigger an interrupt. We will start to talk about interrupts at the end of this lecture. So you really don't want to set a timer and just sit there and go, did you reach the number? Did you reach the number? Did you reach the number? You would really like it to just go off and do some other business, and then when it's done, let you know. That's the major purpose of an interrupt. It can trigger an interrupt to the processor. It can also trigger something on the peripheral reflex system such that it talks to other peripherals, so the processor doesn't have to be involved. You can set interrupts on a variety of conditions: underflow, overflow, comparison between the timer and a fixed value. There's lots of parameters for these timers. If you were taking a look in the application note, there's a general functional diagram of how the timer operates. This isn't everything, but here's sort of the basic idea. In the middle, you've just got some counter, and it's going up or down. That counter is driven by some sort of clock. The clock can come from the processor, the peripheral bus. It can come from other devices. It comes from a variety of places. The counter can also look at some sort of input signal. So whether the input signal is high or low, maybe it counts up, maybe it counts down. Overall, that counter gets compared to some value, and when it's compared to some value, it either outputs another signal, and that can be to another peripheral, that can be to a GPIO pin, or it causes some sort of interrupt. So there's always going to be a clock coming in, there's always something you're going to be comparing to, and depending on the mode you're in, you're either going up or down. If you look at it in a way more detailed setting, this is largely what's going on. You've got your timer inputs. You can detect rising and falling edges. Your clock is coming in here. You can scale it. And the main things you really need to concern yourself with are these registers up here that do the sort of the command and control of the timer. So the important ones are count, top, and counter control. And sometimes you can compare to some value for overflow. You can compare to 0 for underflow. You can compare to arbitrary values. As we mentioned, you can drive the clock from multiple sources. Inside the documentation, you will see clocks referenced sort of in this syntax here. This is HFPR clock timer. So that means high frequency peripheral clock for the timer. That clock is derived from the high frequency peripheral clock, which is then derived from the main system clock. There is a ton of cascading clock chains in the processor, and we'll deal with them lightly, but generally we will not mess with clocks. The important point is that that clock can be scaled. So let's say that I want my peripheral bus to operate as fast as I want. Let's say I want it to operate in a megahertz, but I don't want my timer to tick away at 1 megahertz. That means it rolls over really quickly. So you may want to scale that clock such that your timer operates slowly. If I'm trying to time 5 seconds and I only have 16 bits and it's going at 1 megahertz, I'm never going to be able to really time 5 seconds. So you want to be able to scale that clock to make sure you don't overflow your timer. Basic modes, as I mentioned, and let's be particular about these keywords. In the up mode, the timer starts at 0 and goes up. Once it surpasses the maximum value that's in top, it causes an overflow event. So remember, when a counter or a timer goes up, 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 and then exceeds the maximum value, it causes overflow. Down is the opposite of that. It starts at the top value and counts down, 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 down till 0, and then it underflows. So overflow means I've gone too high and I wrap back around. Underflow means I've gone too low and I wrap back around to the top. This is always going to be unsigned math. There's no point to have a signed value in a timer. So if you've got 8 bits, then you have 2 to the 8 minus 1 values that you can count. Some other modes are up, down. This is where the timer goes up to a limit and then back down, and up to a limit and then back down. So it just oscillates between 2 fixed values. Well, it oscillates between the top value and 0. So when it hits the top value and turns around, you get an overflow event. When it hits the bottom value and turns around, you get an underflow event. A final mode we might deal with is called quadrature. That's a really weird thing to say. It's for measuring rotary encoders, quad encoders. Those are sort of square signals that are off in phase, and it'll automatically measure sort of the phase for you. And you'll find rotary encoders on things that do wheel speed. So Jason for Capstone needs to know that. So things that do wheel speed and spin, these are these square waves, and you want to know the time between the edges of the square waves, which implies how fast the thing is spinning. And you don't want to write software for this because it's annoying. You would rather just set up the quad encoder to do it for you. So in the quadricoder mode, you've got two signals that are out of phase, and you want to measure what's the time between those edges. As we mentioned sort of in the big diagram, timers can capture external data. They can look at external pins and see if they're low or high and measure the time between rising and falling edges. And related to PWM signals, you can either capture some information, which means that you can sort of capture when an edge happens, and then you can also kind of compare it to different values to cause your output pins to change. So capture is kind of reading in some data, and compare is looking at your current timer value to some sort of data value and then doing something with it. We'll talk a little bit about this when we get to PWM modes and how you can generate PWM signals of an arbitrary duty cycle. And you would rather do this in hardware than software because you just want to set up the timer to do PWM. And as I said, you can use a PWM to sort of fake any sort of analog voltage you want. So if you want to make your LEDs dim or bright and you want to make them vary in intensity, PWM signal. If you're controlling some sort of motor that's rotating around, it is going to be a PWM signal to set the position of that motor. So if you're dealing with motors, if you're dealing with lights, probably a lot of other things, there is a bunch of PWM stuff in that. One question you might encounter when using a timer is you're going to use a timer to generate an arbitrary waveform. So think if I'm doing analog to digital or digital analog conversion, I want to generate some arbitrary function of a certain speed, of a certain accuracy. If I have to know what's the fastest waveform that my timer can generate, what's the fastest sort of frequency wave I can generate, what are some things that are important when I'm trying to think about that? So if you're trying to generate the fastest square wave with the fastest frequency that you can, what factors in your hardware are important? Felix, what do you think? An idea? Okay, so if we've got really cruddy transistors, if we have a really poor design, then we can't actually switch very fast. Think about this. What on this diagram helps me figure out how fast maybe I could switch on and off? Darren?
Your clock speed.
Right, so if this clock is going at 1 hertz, is there any way I'm going to generate a 10 kilohertz wave? Right? The number of bits that I have matters. It's how much I can time. If I've got a super fast clock, but I can only store like 2 bits, like I'm not going to have the resolution I need to store all of my values. So some things to consider when you're trying to pick, when you're talking about a timer and you're trying to pick how do I use it, what properties do I need, is what clock sources does it have? What modes can it be in? How many different places can I drive that timer from? If I have a really fast clock, can I scale it down? Can my timer be driven by an external clock? Or does it have to be an internal clock? What is the maximum frequency of the processor? If I'm on a really 1 megahertz processor that's really slow, am I going to really be able to communicate to something that's trying to generate a 20 megahertz wave? What's the maximum value I can represent? How many bits do I have? And how many interrupts do I have? Can I only do underflow? Can I only do overflow? What sort of events can I respond to? Questions so far on timers? Travis?
So what was jitter again?
Jitter is sort of, do my bits oscillate, and is it going to be stable as I'm sort of reading data in? Can I capture it? Don't worry about it. Jitter is an old phone you give to people. It's a jitterbug. So think about it this way. You've got a 16-bit counter. You've got a 16-bit timer. How long can you use that to time? And it's based on a variety of different factions. So as an easy example, let's say that you have a 3-bit counter that's getting incremented at 8 hertz. So 3 bits means I can hold 0 to 7. And so if I go 1 second, 2 seconds, 3 seconds, on and on and on, I will overflow once I hit this value here. So once I make this transition, I will overflow. So the amount of time that I can measure is equal to the maximum value I can hold, sort of plus 1. So it's 2 to the n bits. So it's the maximum value I can hold plus 1 divided by how fast I'm doing it. So I can go 1, 2, 3, 4, 5, 6, 7, 8. And I'm doing that at 1 hertz. That means I can measure out like 8 seconds with this counter. Now, it's sort of funny when I say it's the maximum value plus 1, because the maximum value you can hold is 2 to the n minus 1. So this is 2 to the n minus 1 plus 1. So you can also just think it's 2 to the number of bits divided by the frequency. But I leave this in here because when you are loading values in the timer, you're going to actually be putting in a top value, and so that needs to replace that max value location. So you're actually going to put a value in a certain register in the timer, and that's what it's going to be compared to. So in general, for your timer, it can measure the amount of time equal to the maximum value divided by the clock frequency. It can measure up to 1 million values, and you're doing 1 million values per second. You can do 1 second of timing. This is an important thought, and a lot more is going to be based on this. Questions on how you figure out generally how long a timer can count for something. All right. Now, some of this stuff is fixed. Some of this stuff can be modified. The maximum value of your timer is generally fixed. It's a 16-bit timer. You don't have any extra bits. You could cascade your timers together, but in general, you're going to have a single timer, and it's fixed. When we have sort of this equation here, when it's count frequency, remember that the frequency that drives the clock is not fixed. It is modified by a prescaler. So your time is actually the maximum value plus 1 divided by the clock frequency and then divided by that prescale value. So if you were going to write out the time, then it's sort of t is equal to max plus 1 divided by frequency divided by your prescale. So if you don't scale your clock, then you're just dividing by if you don't scale your clock, you're dividing by its frequency. Let's say you scale the clock by 16. You've now cut down the clock speed by 16. If you slow down the clock, that means you can count for a longer amount of time. So you've only got 2 to the 16, you've only got 16 bits, and if you're banging away at them fast, you're going to count a small amount of time. If you slow down the clock, then you will count for a longer amount of time. Bill, you look confused. All right? Do this real quick. Assuming you've got a 16-bit counter, it operates naturally at 25 megahertz, but you're going to scale it by 512. What is the maximum amount of time that can be counted with that system? So take a minute, do the math on that one. All right, let's take a look at what some folks got. Kevin, give me a hand here. Did you think you got the right thing?
I
All right. Well, let's plug it in this way. If I have a 16-bit counter, what's the biggest value it can hold?
Biggest value is 65,637.
Right? So that's 2 to the 16 minus 1. That's the biggest value it can hold. And we're going to say plus 1. Okay? Felix, what's the clock frequency I'm operating at here? All right, it's 25 megahertz. So 25 times 10 to the 6. Remember, mega is 6. And then Felix, how much am I scaling it by? A factor of 2?
So, I mean, I thought it was a scale that was
So when I talk about a prescaler of 512, that means I'm going to take the clock and I'm going to divide it by 512. So I'm going to cut it down. So if you punch all this math in, you've got 2 to the 16 minus 1. That's the biggest value that timer can hold. Plus 1, so these are a wash. 25 million. So the way you want to think about the frequency is, I think Michael asked us this in seconds. And that's actually a pretty good question. Because this is sort of unitless, like this is just a number. This is, you want to think of as 25 million things per second. So this is the only thing that actually contains a unit. Divide that by 512, you get roughly 1.34 seconds. The major thing here is that this has a limit on it based on hardware. This and this can be scaled. So you're going to have some problems later on labs and on exams where I'm going to say, make a timer count this amount of time. And you're going to naturally look at it and it's not going to work. And you're going to have to change both of these values to make it work. So, going back to the discussion about PWM, you can use a timer to make a square wave. Square waves can drive things. There's a couple ways that you can decide to sort of use a timer to toggle a pin, and there are actually sort of a couple of dumb ways to do it, but we want the timer to do it automatically. I could set a timer, and I could just look at it through the program. I could compare it to a value. I could toggle my pin. That would sort of be a waste of time because we want the timer to operate and do this on its own. So if you're trying to figure out what's the biggest, fastest sort of square wave that you can generate, you want to know sort of what's the smallest amount of time or sort of the largest amount of time that you can calculate. What we just went over is that time for a counter is the maximum value divided by the frequency divided by the clock. If you want, that's the maximum amount of time it can calculate. If you're trying to figure out, if I use that to make a square wave, let's say every time the timer pops, I toggle a pin, I can then use that to make a square wave. If you invert this expression, then the maximum frequency generated by a pin is equal to the frequency of the source clock is equal to the frequency of the source clock divided by the scalar divided by sort of the maximum value plus 1. Jason. Let me show you the line. The practical answer is that this clock right here comes directly from the peripheral bus. If you slow this down, you will slow down the bus for all peripherals. You don't want to do that. So instead, there is one major peripheral bus line that comes through here, and they break off a single wire, and that drives your timer. You don't want to slow down the whole highway for everybody, so you slow down it individually. That's why. It's based upon their construction. At the clock generator, you could manually slow down everything, but they build it into this module because it makes an easier design. So they build a bus, they send all of the clocks to all the devices, and if it's too fast, they let the device deal with it. It's sort of an abstraction that they hide away so that that decision doesn't impact the overall bus. That's why. Good question. Now, here's going to be an important point if you're going to try to generate a wave. That calculation right there takes our time period of counting through an entire why can't I say entire timer? That's actually really tricky. This is sort of, if my timer just counts up, this is the maximum frequency it'll count things at. And so you might say to yourself, well, I want to generate a square wave, and every time that timer pops, I'm just going to toggle a pin. And that'll guarantee to give me a square wave with that frequency right there. And it's not going to do it. You're going to be off by a factor of 2. Because if you wait for the timer to go up and then you tick it, and then you wait for the timer to go down and tick it, you're going to be off by a factor of 2 in generating your square wave. Think about it this way. Think about if I wait some period and I toggle my pin, and I wait some period and I toggle my pin, 2 time periods have gone past, so my frequency is actually cut in half. My frequency is not 1 over that simple period. So if you're trying to generate a square wave of 90 hertz and you use this equation, and if you're trying to generate a square wave of 90 hertz and you use this equation to figure out what value to put in the timer, you're not going to get a 90 hertz wave. You're going to get a 45 hertz wave because it's going to go off, and then you're going to tip it once, and it's going to go off, and you're going to tip it again, and it's going to be off by a factor of 2. Questions on this? If you actually want to generate a wave of a certain frequency, remember you need to take these time periods and you need to cut them in half. And so what I've done here is rearrange all the lovely math for you so that if you actually want to generate a wave of a certain frequency, you have to then solve for the value here that you put in your timer to toggle the pin. You basically just do it twice as fast. Because if you wait to go up and then you wait to come down, you will have a wave that is half the frequency that you desire. And if you want, you can compare this to the equation in application note 14. And I do that right here. So, if you look in the application note and it gives you an equation for how fast a wave can be generated, you will get this. And then if you come back and you look at my notes, you'll look at this and you'll say, what the heck, Dr. Forsythe, you lied to me. It's the wrong equation. It's the same equation. It's the same equation. I just represent these quantities differently. So in my equation, here is the incoming clock frequency, FC. Here is their incoming clock frequency here. This is my idea about the maximum value plus 1. Here's their idea of the maximum value plus 1. The major difference is that here I represent the prescale as an integer, meaning I do it as a prescale of 1, which means don't do anything to the clock. I do it as a 2, which means cut the clock in half, and so on and so on. Here, they are representing the prescale as raw bits that go into some register's configuration. So, in the application notes, what you will find is you will find expressions like this, and this is a raw number, but this is actually some sort of configuration bits. So if it's printed in all caps like that, it's a binary value. So inside the data sheet, if you put a 0 for the prescale, it gets to be 2 to the 0 plus 1, which is the same as not scaling the clock. So for them, putting in a prescale bits of 0 means do not scale the clock. So in a minute, when we go to the definitions of all these registers, they're representing the prescale as this, and I'm representing it as just a scalar. So when you go back and you read this equation in the data sheet, you're going to put 2 in here, and you're not really going to mean 2. You're going to mean 1. Have a question, Kyle? Okay. As we said, a timer can create a PWM signal of any sort of duty cycle. Your regular square wave has a duty cycle of 50. This one has a duty cycle of 75. This one's got a duty cycle of 25. You don't want to do this manually. You don't want to set a timer and then interrupt the processor and then toggle a pin and then set another timer and interrupt the processor and toggle a pin, because it creates a lot of traffic on the bus that you don't need, and it makes the processor do stuff that it doesn't need to do. It's like having a human do a robot's job. Don't have a processor do a timer's job. We talked about up mode. We talked about down mode. They just count up. They just count down. This is sort of the PWM count up mode. And I'm going to kind of go over this quickly to explain it. The timer can control this output pin right here, this CCX pin. The timer controls that pin. The timer also has 2 other values. It has this CCX compare value, and it has this top value. The basic logic is that when the timer hits the CCV value, it flips. It takes its pin that is controlling low. So when it hits this first line, so the timer counts up, 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 up. When it hits this value, the pin goes low. It will stay low until the timer overflows. So the timer starts at 0. It goes 1, 2, 3, and then goes low. And so if you look at the diagram here, I have 1, 2, 3 cycles of a high value, and then I'm low the remainder of the time. In the next example, this CCV value is much, much lower, and so I'm high for 1 second, or 1 cycle, and then I'm low for 1, 2, 3 more cycles. So 1, 2, 3 more cycles. So by setting the top value, you are dictating how long the wave is low, and by setting the CCV value, you're dictating when the pin goes low, and by setting the top value, you're stating how long it will go low. So if you set the CCV value all the way down here at 0, your pin is low the entire time. If you put the CCV value way above top, it never hits it, and so your pin is high the whole time. So this is how you can set 2 particular registers in the timer, and it'll just automatically generate a square wave for you. You can also, if you want, dynamically update this register and this register, and that will generate an arbitrary square wave for you. And if you can generate an arbitrary square wave, you can generate sort of an arbitrary function if you wish. Why would you want to generate an arbitrary function? Because you're encoding, decoding data. You're transcoding things. You're wanting to send. You have a bunch of digital information, and you have an analog motor, and you want to control it, and it responds to PWMs. Shmity, how much did you guys deal with PWM on the electric car?
On the display, we had a RGB backlight, so we used it there.
Used it to dim it?
Yeah, I mean, aside from that, it wasn't really as much producing analog signals, it was more reading analog signals for the pedals.
And what were you reading analog signals from?
Potentiometers at the base of the pedals.
All right. If you didn't get the rotary encoders or things like that, you weren't doing wheel speed.
No, we didn't get that.
They got it up and running, which was good, which is a good accomplishment. What I need you to understand from this is that this value tells you when to go low. This value tells you how long to stay low. By setting these values, you can get a waveform of an arbitrary duty cycle. Bill?
Do those registers be able to be accessed by the peripheral reflex system?
Yes. I say yes, they should be. I don't know for a fact, but yes. The idea is that some of these registers, yes, are accessible to other peripherals, and so that a peripheral can do some operation and plug the value in.
So your peripheral can give you the duty cycle.
Yes, or another timer possibly could. So let's say I'm trying to copy a waveform. I could have another timer that is timing how long it's low and high, and then I could automatically update it to here or here. Yes, I don't know for a fact that I can tell you which ones, but generally, yes. That's the point of these, why they're memory mapped, is that other devices can then write into them. These are memory mapped things, so anything that can write to memory can write to those registers. There's a longer explanation of that. In the same way that just for completeness, here are the equations if you have your counter in an up mode and then in an up-down mode for generating an arbitrary wave. The only real difference is one's twice as fast, or one's twice as long as the other. Final sort of thing, if you do have the previous example was generating an arbitrary wave. Here you may want to capture and measure an arbitrary waveform. You want to know how long a signal is high, how long a signal is low. There is a mode called clear and start, and that what happens is when there is a rising edge, the timer begins to count, and it counts until the next rising edge. So now you know the width of this pulse. If you wanted to know the amount of time it was high and wanted to know the amount of time it was low, you would trigger it on both the rising edge, on the falling edge, and you could time all of those values and see how long it was high, how long it was low, and measure the duty cycle. So that's my broad summary on timers. We're going to, in a minute, jump into sort of generally how timers work, specifically how timers work on your system. Why do you want a timer on your processor? Why does every single processor include timers? You want to be able to measure time. You want to be able to, at a basic level, have a task occur at some regular frequency. Maybe you have a real-time operating system running, and something is popping every second. Maybe you're a low-power device and you want to wake up every 5 minutes, check the temperature, go back to sleep. You don't want to sit there and poll the whole time. A timer gives you the ability to go to sleep, to wake up, to measure signals, to capture signals. Why do you want to capture signals? Well, you're going to have some sort of sensor that's going to generate a waveform to you. You want to be able to read its data. Why do you want to generate a signal? Well, you're controlling some sort of motor. You want to vary its speed. You want to create an analog voltage. That's why you're going to generate an arbitrary signal. All of this stuff you could do with a processor and a GPIO pin, but it would be really, really annoying. You would have to read the pin, catch the interrupt, sit in a busy loop until something was done, and then do it again. And if you remember our system diagram, the processor is way the heck away from the other peripherals. It's better to have this timer do it on its own and give the data to the processor. The processor is also the major energy hog in a system. If you can shut it down, then you can have your other peripherals do its work. The important things in here are the notion that the timer, it goes up, it goes down, it gets compared to some value, that there's a maximum frequency of a wave it can generate, that there's some maximum and minimum amount of time that it can measure. The PWM and the capture modes will be in there as well, but they're not sort of the main emphasis when it comes to timers. Questions on this? Let me see where I'm going to go. let me go about 5-10 minutes into the particular timers. And then at about 12 o'clock, I will stop, and then we will start. I'll walk around and see where folks are on Lab 1, so I'll give you about 75 minutes to do that. The timers on your processor are just like any other peripheral, meaning that they are memory mapped. They have a certain space in memory in which they live. These timers actually have way more configuration registers than a lot of the other peripherals. There are 34 registers across all of the timers. That's a lot. It's a lot because there are a lot of different modes for these timers. We covered 4 or 5 of them. There's probably 2 or 3 more. The timers can talk to other timers. The timers can talk to other peripherals. There's a lot of information on these timers. We're only going to sort of focus on some of the basic sort of functionality. When I showed you this diagram before, there's a ton of stuff on here, but only 4 of these registers are fundamentally important, meaning that you have to mess with them each time you set up the timer. Which 4 do you think might be important? Kind of looking at the diagram and looking how everything's going. For just basic counting up, counting down, which 4 do I give a crud about? Ben, what do you think? Up here, the prescaler? Yeah, so we care what's coming into here, and we care how much this clock gets scaled. Ben, Lenny, what do you think? Give me another one you think is important. You have a pick of lots of boxes. Pick a box. Yeah, timer top. So remember, the timer is always going to get compared to the value that its current counting value is always going to get compared to some top. If you don't have the top set, it just rolls over when it rolls over. So this is an important one as well. That's some here and that's in here. Nick, what's another one that's important?
The timer CCX.
Where's this? This? Yep, that's the pin. That's the pin that we can control, we can generate things with. Kira, what's like the most important one? Like the big box here where all the arrows are going into it. Right, there's a control register that sets the mode, that makes things go up and down. That's sort of one of the other main ones that you need to pay attention to. So the 4 things you really care about are the top value. Count holds the current value. So this is your register that holds the current value. This is the control register, and this is the prescaler. All this other stuff is in here. It's useful. Bill, to your point, like here are the other inputs that are coming from the PRS system driving things. These are going out to other timers. A lot of this is the PWM and the capture and compare system. This is your basic, up here, timer functionality. And so when the count in the timer is equal to top, you get overflow. And when count is equal to 0, you get underflow. Because the next thing it'll do is underflow. So the 4 major registers that you're going to deal with are control, which selects the clock source and how the timer responds. There's command. So it's not shown on the diagram, but command is how you actually start and stop the timer. So the timer is not just always running. There's a command register where if you write a single bit to it, it'll start and stop the timer. Top holds the top value in the timer. One important note is that there is a buffer register for the top value, because since top is being actively read and used in hardware, you don't want to write to it directly because you could cause a glitch. So there is a buffer register that if you write to first, it'll automatically copy into top. And you will see that on a variety of peripherals, especially on the UART, which is a communication system. You can read and write its send and receive registers automatically, but you might get data in the middle of transmission. You might get data on its way out. So there are generally some buffer registers that allow you clean sort of atomic access to those objects. And then count gives you the current count of the register. when we get into timers, the reason you have a timer is because you want to know some amount of time has elapsed, and you don't want your processor to deal with it. That means we're going to start to get into interrupts. And honestly, interrupts are the main reason you have a microprocessor. Like, you really just want to have your small program, you want to start it up, and then you want things to be event-driven. You want them to be interrupt-driven. So some common conventions that you're going to see when dealing with all of these peripherals is that every peripheral has some sort of interrupt-enable register. If an interrupt is not enabled, it does not occur. It does not occur in the sense that it does not get serviced. Nothing happens. There is also an interrupt flag register. The interrupt flags tell you whether some interruptible event has occurred. That is independent of whether the interrupt is enabled. So if the interrupt, even if the interrupt is disabled, the flags will still get set. So if overflow occurs, but you don't have the overflow interrupt enabled, the overflow flag will still go high. When a flag goes high, you're going to need to clear the flag. Otherwise, your processor is going to sit there and go, oh crap, it's overflow, oh crap, it's overflow, oh crap, it's overflow, forever. That is a common mistake. I can guarantee when you start to do work on timers, you're going to forget to clear the flags, and you're going to sit in your interrupt handler forever. If an interrupt occurs, your processor is not running its main program. Interrupts occur in sort of a privileged space. Just like all of your other peripherals, the timer has all of these in a control register: control, command, status, interrupt enable, and IF. So IN is the interrupt enable register. IF is the interrupt flag register. And when you are going to set up your timer, there are 4 things that you've got to do before you actually configure it. You've got to pick what clock it's coming from. Is it the peripheral bus? Is it another timer? Is it an external clock? You've got to select how much that clock is then scaled by. It's going to be some power of 2, so 2 to about 1024. What mode is it in? Is it going up? Is it going down? Is it going up, down? Is it in quadricur? Is it in for wave counting? Whatever mode it's in. And then for our particular application, you want it to be in debug run mode because you're going to be debugging your processor, and you want the timers to run while you are in the debug mode. And when we come back on Monday, we're going to fill out a nice little table that helps you figure out how to set up your clock, or set up your timer. This sort of method is a good structured method for figuring out how to configure a peripheral. So what generally I will do for you in the initials is I will tell you like what things are important, what things need to be set. Later on, you'll have to figure that out. But then once you know what things need to be set, you need to figure out what setting you want it to, what bits is this setting in that register, and then what hex value do you want to set it to. So is controlling the clock in this register bits 0 through 3, bits 9 through 12, like what bit range is it? And then once you have that bit range, what value do you set it to? It's the same thing you're doing with the GPIO. You've got to set the mode. Well, is the mode 0 through 3? Is it 4 through 7? What bits are the mode? What value do you want to set it to? So throughout the notes, you'll see this kind of table that sort of lays out all this configuration. That's sort of the tedious part of the processors, is figuring out all the different configuration bits. So I'm going to stop there for timers, and I will then walk around, and I'll give you guys the next good hour 15 to work on Lab 1. Please really make sure you're getting down to like the pointer math ones. This will sneak up on you, and it'll get you unless you're working on it now. So those are my comments. That's what I got.